In this class, we are basically going to discuss more about abstract algebra. So in my previous class, I have already discussed about this equivalence relation. That means we had the properties like symmetric, reflexive, and then transitive. If all these three properties are satisfied, then we call that relation as an equivalence relation. So in my previous class, I gave one problem. The problem was like this. Suppose A is a set. Say I'm just changing this problem. Suppose A is a set having four elements, 3 and 4. So my question is how many reflexive and uh, symmetric relations are there? Symmetric relations are there with say 1 1 2 1 as a subset. Okay, so the question is clear. So here my base set is this four elements. So the question is how many reflexive and symmetric relations on A are there with this as a subset. For example, suppose if I consider this like relation row 1 equal to say 1 1 1 2 sorry 1 1 2 2 3 3 4 4 and then 2 1, then suddenly this is a reflexive relation. Why? So because it has already all the diagonal elements. In my last class I have already mentioned, and it also satisfies this property because this subset, so this is a subset of A cross A, and it satisfies this property like this is a reflexive relation which contains this as a subset. So 1 1 and 2 1 are already there here, 1 1 and 2 1. Okay, so they are the reflexive set, reflexive relation on A having this as a subset. Similarly, if I consider row 2 to be equal to 1 1 2 1 and then 1 2, then you can see that this is again a subset of A cross A, and it has this as a subset. So here also we have this as subset. So this one and this one. Sorry, not this one and this one. Okay. So these two elements are already there. Now the question is row 2 symmetric? Question, is row 2 symmetric relation? What is your opinion?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Okay. So yes or no? So most of you mentioned about this is a symmetric relation. So it also contains this as a subset. So now my bigger question is how many reflexive and symmetric relations on A are there with this as a subset? So that's a question that may be asked for any kind of competitive exam, and it's not very difficult. And if you are able to solve this, then I am sure that you will able to understand what is the proper definition of reflexive symmetric definition. So I think it's very easy to do. Please try it. Otherwise, I will do it maybe in the next class. Okay. So that part is done. So I think the symmetry relation part is almost done. So where I started with? I started with the definition of a group. So where I said that this is said to be a group. G and dot is said to be a group where G is a non-empty set and composition is a binary operation satisfying few properties like this is, what are the properties? This is associative, existence of an identity element, identity, and the third property is the multiplicative inverse property. For each element, there exists a an inverse. So broadly speaking, and I discussed everything in my last class. So one may certainly say that I have missed one property, that is the closure property. Closure property. And as I mentioned in my last class that if this is already defined as a binary operation, then there is no need to mention about this closure property, because from the definition of binary operation or binary composition, it's clear that this dot or this composition is nothing but a mapping from G cross G to G. And from the definition of function, it's clear that if this composition is applied on two elements A and B denoted by A composition B, then from the definition of function it must be within G, and that is nothing but the definition of closure of this composition. That's why if I mention like binary operation on G, then there is no need to mention about the closure property separately. It's automatically included. Okay. So now let us try to. So this whole topic is basically based on the abstract algebra, and in this course I will also discuss something more problems that are usually come in some competitive exams, starting from JAM exam to ISI exam to TIFR exam to NVHM exam and all. So I will discuss all the things in details during this class or during this course. Okay. So let us try to think about some of the examples. For example, if I have G different sets. So let's start with G to be say my natural number with respect to addition. The question is this a group? Yes or no?
No.
So this is not a group. Then what is the problem that it happened? Why it's not a group? So there are three properties. Which property it violates?
Identity.
So somebody says that identity,
Identity inverse.
Inverse identity দুটো
inverse and identity both. Okay, so it actually violates 2 and 3. Okay. Now if somebody says if I consider say z with respect to minus, will that be a group?
No.
Which property that it fails?
Associativity does not mean.
It's a associativity would be a problem. So 1 would be a problem. And if I consider z with respect to dot, then
Inverse of 0.
Inverse does not exist.
inverse of 0 or inverse of 2. So the third property could be a problem. Okay, if I consider say q with respect to dot, then q means set of all rational numbers with respect to dot. Then
Inverse of 0 does not
Inverse
exist.
of 0 does.
okay, so the inverse, that means 3 is also a problem with respect to 0. Okay, now if I consider positive rational number with respect to multiplication, then positive rational numbers with respect to multiplication.
It forms a group.
So for the first time now we are seeing that all my previous examples they fail to be a group, but here q plus it forms a group. forms a group. Okay, so let us try to see what are the properties, like what are the identity element. What is the identity element of Q
One.
plus? 1 is the
One.
identity element. Okay, and if I consider any element like half, then what would be the multiplicative inverse of half? 2 is the multiplicative inverse because that becomes 1. So now we are sure that it's a group. Okay, if I consider all non-zero rational number, so that means this is equal to Q minus 0 with respect to dot. Will that be a group?
Forms a group.
Okay,
Forms
and
a group.
somebody says this forms a group. Okay, with the almost similar properties. Now, if I consider R with respect to dot, will that form a group?
No.
No, sir.
Why not?
If inverse of 0 does not
Inverse
exist.
Okay, so again, the third property, inverse of 0. If I consider, say, R positive number with respect to addition, positive reals with respect to addition, will that be a group?
Sir, identity
No.
does not exist.
It will
No,
have a
sir.
No, sir.
problem. Which problem? Which point? One,
Identity.
Say inverse.
Identity does not.
Identity does
Identity and
yes, identity element. Because here, if I consider positive real numbers, then 0 will not be an identity. So 0 not present. So it's also not a group. Okay. Now all these groups, now if I try to extend this, so if I try to extend this list, maybe we can have complex numbers, say with respect to addition, and say non-zero complex numbers with respect to multiplication. Now I have taken these two. Will that form a group, form two groups? What is your opinion? Complex number with
yes,
respect to addition,
yes, sir. They forms a group.
it forms a group,
Yes, sir.
and here
yes.
complex. So this is also
Yes,
a
sir.
group. To like natural number, then we extended it to Z, and then Q, Q plus, Q star, and so on. So there are plenty of such examples where they form a group. Now, there is one important term in group theory that we are going to define here is order of a group. Order of a group. So, what do you mean by order of a group? Can anybody tell me what do you mean by order of a group? Order of a group.
Elements present in a group.
Very good. So, it's nothing but the number of elements, the number of elements in the group. So surprisingly, all the groups that I mentioned here, which actually form the groups, are all infinite order. Now, among these infinite things, I think, have you started with this cardinal number and all? Any idea about cardinal numbers? Okay. So for example, if you consider Z and if you consider R, for example, so both R and Z contains infinite number of elements, right? Now, if I ask you the question, okay, for example, if I ask you the question, set wise, as a set, which set is bigger? Okay, if I ask you a question as a set, which set is bigger? Set of all natural number is bigger than the set of integers, or the other way around, or they are of equal number of as a set, not as an element, number of elements. I am considering as a set. Which set is bigger? If I ask you this
Z
simple
is
question,
bigger. So Z is bigger because Z
so
Set of
contains.
apparently,
integers.
So set of integers is bigger.
Set of
okay,
integers.
so that means according to you, the set of all integers must be bigger than the set of all natural numbers. That means bigger in that sense, the number of elements here must be more than the number of elements present here, according to you, right? Okay. That means, for example, very easily you can say that 2 belongs to Z, but sorry, minus 2 belongs to Z, but minus 2 does not belongs to N. So all elements of N must be within the set Z, right? Now there is a important term in mathematics which is known as cardinality. Cardinality of a set. That means if you have two infinite sets, so both of them are infinite sets. Now how do you compare about how many elements are there in that group or in that set? For example, if I consider R the set of all real numbers, then you can certainly say that this must be bigger than all these sets. R must be bigger than both N and Z, and intuitively you may think that R must have more elements than the number of elements present in Z or even N. Okay, so there is a very important term in mathematics that is known as cardinal number. So in my class, I'm not going to teach you about this cardinal number, but certainly one may think that if you can have a bijective correspondence, say between the two sets, then apparently you can say that both of them might have the same number of elements. For example, suppose I have one set 1, 2, 3, and there is another set A, B, C, and I have given a correspondence like this, a function I have defined like this: 1 goes to A, 2 goes to B, and C goes to 3 goes to C. Then you can understand that this is a bijective function, maybe from a set A to B. So f of 1 equal to A, f of 2 equal to B, f of 3 equal to C. That means it's a kind of bijective mapping. Now we can say that this F suddenly is a both injective as well as surjective mapping. Since both of them are finite, A and B, it's easy to visualize. But what will happen if both the sets are infinite? Then you may not be able to define in that way individually, because there are infinitely many elements. So there, this cardinal numbers and how to define such mappings play an important role. And you will be surprised to know that though as a set N is a subset of Z, but they contains equal number of elements, and that's quite surprising. So it's a kind of maybe a first shock to all of you who are now studying this analysis, or now studying this real analysis and cardinal numbers. For them, they may think that how can here minus 2, minus 3, minus 1, these elements are there, and in N you don't have those elements, then how can the number of elements of N is same as the number of elements of Z? Now what's about the number of elements of Q? And then what's about the number of elements of R? Then how to define them? And all those things are, these interesting things are very much studied in the theory of cardinal numbers. And I'm sure that in your this semester or maybe in the next semester, you will certainly come across with these ideas. So, okay, so there, for the time being, I can assume that all of them, they are all infinite sets. So they are all infinite sets, okay? But as I mentioned, among these infinite sets, there are some discrepancies are there. So some sets are bigger in that infinite, that means bigger than the others. For example, you can say that the number of elements here must be bigger than this, but the number of elements in n and z are exactly the same. That means they have some kind of equality, and sometimes some sets are not equal in terms of the number of elements. So these types of things are very important, and suddenly we will get all those things in details in your final or in your subsequent courses. Okay. So I am not doing all those things, but for me now, for the time being, both of them are infinite. Okay. So the question is, how can I, so all the examples that I have already given to you are all examples of infinite groups. Now, can we have some example of finite groups? Okay, finite groups. Okay. So before going into much details, let us try to solve few of the problems. Okay. So, and here you will understand that this abstractness comes into play. Okay. Let's start with a triangle, equilateral triangle. That means the size of each side is same. Though it's suddenly it's not an equilateral triangle, but for mathematician they can assume anything. So assume that, okay, it's again badly drawn. Okay, maybe a little better. Anyway, so for mathematician we assume that this is an equilateral triangle. That means the length of each side is same. This is a design on a cake. Suppose this is the whole cake is there. So this is the whole cake, and some triangular design is there on the cake, which is an equilateral triangle. And let us try to write the names. Suppose I have written 1, 2, 3, and suppose I have cut it down this portion of the cake. If I lift it out, then there will be a gap here. If I cut the cake and lift this part out of it, then there will be a gap, a hole here. Then I just put the portion that I have cut it into that gap. That means again this 1 will come here, 3 will come here, and 2 will come here, right? That means I have just taken this portion out and I just put it back here once again. Then 1 remains 1, 3 remains 3, 2 remains 2. And I call this operation as E, just a name, E. And I write it like this also. 1 goes to 1, 2 goes to 2, and 3 goes to 3. Now this thing may happen in another way. For example, suppose this is my equilateral triangle and it was 1, 2, 3. And you can rotate, since this is an equilateral triangle, you can rotate the whole thing, whole cake, by how many angles? What should be this angle? So that it will suddenly fit into this portion. What should be the angle size?
60 degree. 60 degree.
60. If you rotate it by
120.
60,
120.
yes.
120.
Okay, so if you rotate it by 60 degree, then what will happen? 60 degree means say something like this. 1 will come here, maybe 1 will come here. It will not fit into the hole. But if you rotate it by 120 degree, then suddenly this cake will fit into inside this hole where you have some gaps. So that means here you had initially 1, 2, 3, and now 2 will come here, and then 1 will come here, and 3 will come here. So you can write in this way. So I call it a rotation through an angle 120 degree. And so in short, I write it only by R. And that can be written in this way. So 1 goes to, so 1 goes to 2, 2 goes to 3, and then 3 goes to 1, in this way, right? Now you can also do another operation, like, so you had this, so initially you had 1, 2, 3. Now how many angles that you want to rotate it so that it can fit inside this hole? How much?
240.
240.
240.
240. So I call it, so actually I am rotating twice, right? So here one time rotation means it's a rotating by angle through an angle 120 degree. Now I am rotating it through an angle 240 degree. That means I am applying R twice. So I call it as R square. So initial first R and then again R. So it's an R square. So after doing that, what will happen? One will come here. So after one rotation, one will come here, then here. So one will come here, 3 will come here, and then 2 will come here. So in terms of this notation, it becomes 1 goes to 3, 2 goes to 1, and then 3 goes to 2. Okay. So any other symmetry that you can find it of, so that the cake may come into this proper place. It may happen that this part may go at the end, I mean at the bottom, and the bottom part may come up. So any kind of operation, that extra operation that you can think of. Okay. Yes, tell me.
Sir, reflection.
Reflection. Very good. So if I consider reflection about this axis, maybe say this is my equilateral triangle. So 1, 2, 3, and I could have a reflection about this axis, right? So after reflection, what will happen? 1 will remain here fixed, 2 will come here, and 3 will come here, right? So I call it as reflection or flip. So flip about 1, 3. Sorry, flip about this axis. I call it F1. Okay. So how to write it in terms of this? 1, 2, 3. Once 1 remains fixed, 2 goes to 3, and 3 goes to 2, right? Now I can have another, for example, like this, and then access through this. So here initially 1, 2, 3 was there, and now after rotating this, after flipping it, it becomes 3 will here, and 1 will come here, 2 will come here. So as a result, I can write it like this: 1, 2, 3. Here 1 goes to 2, 2 goes to 1, and 3 remains the same, right? 3 goes to 3. Now this can also be done with this. Okay, and I call it, this is F2, and I call it this as F3. And initially it was 1, 2, 3, and after rotation it becomes 2 will stay remains the same, and here 1 will come and 3 will come here. So as a permutation, can anybody tell me what shall I write here?
3 to 1.
This is 2 remains fixed and 3
3 to 1.
to 1. Very good. So here we have all these operations. I call it F. Now we say that they are the all possible symmetries that we can have on an equilateral triangle. Okay. Now let us try to summarize what we get. We had total 6 operations. First one is E. Then we had R, that means rotation through 120 degree about the origin. Then we had R square, right? Then we had F1, then we had F2, and then we had F3. So total 6 elements. Okay. Now let us try to find some of the relations between F1, F2, and F3. Let us try to find. Okay. So what is F1? So F1, if I have like this, uh, say, okay, let's say what is our FR? Okay. And then what is our FR square? So what is FR? So FR means, so here R is on the right and then you are applying it on that R, this F. For example, when you have some function, say F and G are two functions are there. How do you explain this? Say, suppose you have a function F from A to B and G from B to C, then how can you define G composed F? So this is basically G composed Fx should be like G of Fx. Why? So G composed F is basically a mapping from A to C, right? So this is a mapping from A to C. It's clear? That's why I have written like this: G composed Fx equal to G of Fx. So similarly, here also we have Fr. Fr, that means it should be applied on a triangle. So initially I had triangle means 1, 2, 3. Now how it operates? It operates like F of R of this triangle, R of this triangle, 1, 2, 3. And how the rotation transform this triangle? The rotation transform into 120-degree turn. That means it becomes 2, 1, 3. And then I have, so it say it is F1. Okay, say this is F1R. So this is F1R. So this is F1. And F1 was, how was my F1 defined? My F1 was defined like this. So it has to be a vertical about this axis, the reflection. So how do I define then? Then about this axis. That means 2 will remain fixed. So ultimately 2 will remain fixed, and here I have 1 and 3, right? Now just have a look at, starting with 1, 2, 3, what makes you 2, 1, 3? Let's see. Starting with, so it resembles with this, it resembles with this figure. So it's 2, 3, 1. And at the end, we also, okay, no. So it resembles with this, not this. Sorry. It resembles with this. Uh, Sorry, it's a 2, 3, 1. Okay, let's see. 2, 3, 1. Right? Okay, so it's 2, 3, 1. It's not same as 2, 1, 3, right? 2, 1, 3 is not present here anywhere. Anyway, so now let us try to think about what is RF. Can anybody tell me what is RF of 1, 2, 3? Exactly same way, can somebody write it down? What is RF of 1, 2, 3? So you can put it 1 here. Same way. So initially I will do, so it was F1 first. That means it will come like this. That means R of 1 will remain the same, and here it will have 2, and here it will have 3. Okay, and if I just rotate it to an angle 120-degree, then 3 will come here, 1 will come here, and 2 will come here. Now let us try to see it resembles with what? It resembles with F3. The same thing here. 3, 1, 2. That means R of F1 must be same as F3. Is it clear? Any doubt or question? Please let me know.
স্যার F1 প্রয়োগ করা মানে তো 1 টাকে ফিক্স রাখা।
Yes, the vertical one, not 1, the vertical one. What is F1? F1 is nothing but this one, the vertical. About this axis, you are taking the flip. So here also about this axis. So here F1, so 1 remains fixed, 1 is unchanged, 2 and 3 are changed. And after that, you are making a rotation, right? So a rotation through an angle 120 degree. So the 3 will come here, 3 will come here, 1 will come here, and 2 will come here. And that's the thing. And that is nothing but your F3. So what do you get? You get F3 is nothing but RF1. Now can tell me, somebody tell me, what is R square F1 of 1, 2, 3? Quickly, somebody tell me, what is R square F1 of this? So R square F1 means R of R F1 of 1, 2, 3, right? And just now I have seen that RF1 is nothing but this triangle. So that means this value, if I put it here, then this is a nothing but rotation of this triangle 3, 1, 2. And if I just rotate it once again, that becomes 2,
3.
3, 1. And what is that? 2, 3, 1, 2, 3, 1. And that is nothing but F2, right? So what I get? This is nothing but R square F. Okay. So now you see that this set becomes, I can now write this set as E R R square F1. This is nothing but R square F1, and this is nothing but R of F1, right? Now if I just omit this F1, just write it by F. F means the flip of this line, flip against this line. Then how can you write it? Like E R R square F. I just write it first RF and then R square F. So now you can see that we started with how many symbols? 1, 2, then R square maybe with R, then F1, F2, F3. And now it becomes E, R, R square and F. So now it becomes E, R and F. So 3 symbols are there. Now the question is, what are the relation between them? Okay. So let us try to find out the relation. If I start with this rotation, so initially we had this rotation. So R, if I rotate it through a 120 degree, then this R. If I rotate it by 240 degree, then it becomes R square. Now the question is, what will happen if you rotate it by 360 degree angle? 360 degree angle. Then it suddenly becomes R cube. Okay. And what it will look like? It will suddenly look like this. Then again, if I rotate it by again 120 degree, then 1 will come here, 3 will come here, 2 will come here, and that is exactly the same thing. That means this is nothing but R3. Okay. So R3 is nothing but E, the initial one. That means you have just taken it out and then you put it back at the same place where you had the hole. That means 1 goes to 1, 2 goes to 2, and 3 goes to 3. Okay. So that means here you have now R cube equal to 3. Now what's about F? So F is here, the flip, sorry, F is here, the flip against the vertical line. That means here like this. F was like this. So 1, 2, 3. And it was F. Initially I started with F1. Now I just replace F1 by F. Now if I have F square, what will say? it will again flip. So f means it will come here, it will come here, and f square means it will again come here and it will again come here. That means it will the initial phase. That means f square is also e, right? So now you get lots of relation. So you started with a set and then few symmetries, and you ends up with few things like e, r, r square, f, rf, r square f. So there are 6 elements, 1, 2, 3, 4, 5, and 6, and you had few relations more like r cube equal to e equal to f square. Okay, now we'll again see few of more extra things like what is r square f and fr. Okay, so let us try to find out, is there any relation between these two? So r square f, and if I have 1, 2, 3, just now we have seen that what is r square f? It's basically, just now we have drawn this. So r square f, it is nothing but 2, 3, 1, right? It's 2, 3, 1. It's 2, 3, 1. 2, 3, 1. Now let us try to find what is this. 1, 2, 3. Can quickly somebody tell me what it will be? I think I have already made this fr, yes, fr. I already made this. Fr is nothing but 2, 3, 1. Fr. I have already made this, and that is 2, 3, 1. 2, 3, 1, and the same. Both the triangles are same. That means what is your conclusion? Your conclusion will be r square f should be equal to f of r. That means you are having this set with too many relations are there. Among the one relation is this is another relation, and this is another relation. Okay, now we are going to show you very interesting properties. Okay, so now I can forget all the images and all. Now we are in abstract algebra. That's why it says it's abstract. So you don't need to think any images and all. So you are having basically these properties. That means I am having a set, say G equal to E R R square, RF R square F, sorry, F was there, F RF R square F, and having your relation R cube equal to E equal to F square, and R square F equal to F of R. What I say, that this is a group. This is a group with respect to the operation that just now you have shown. Just now you have seen few of the operations like rotations, reflections, and all. I say that with respect to this forms a group. This is a group. So few conditions we need to check first. What are the conditions? The conditions are, we need to find that if I do composition of any two elements, that will suddenly be within that G. So that's the closure property, right? So can you tell me, anybody tell me any two elements that I should take from here? Anybody? Somebody tell me any element, any one element.
R,
Huh?
R,
R. Okay. So if R is there, then if it will be a group, if it will form a group, then suddenly R square should also be here. You can see that R square is already there, right? You should, it must be R cube must also be there. Is R cube is there inside?
yes, sir.
R cube is also there because R cube is E, and that is also there. So whenever you, if I ask you R to the power 14 is there, is R to the power 14 here?
Yes, sir.
Why?
like we can do it like r to the r cube, then r to the power 6 equals to e, like that we can find out what is r to the power 14 also.
Yes. So can you quickly tell me what is r to the power 14 is?
R squared, sir.
R
Yes,
squared.
r square. Certainly, because r to the power 12 and then becomes r square. Okay. Now take any composition of two elements. Can you tell me any two elements from here? Say, make it little complicated. Say r
R,
square f whole cube. Now the question is, if this is a group, then certainly this will belong to this group. Now let us check how it is happening. So how to write this? R square f cube means you are basically multiplying it 3 times. That's why it's cube, right? Now apply the associative property or shifting of brackets. So it's basically, or you can, if you say that, okay, it's not yet group, you're going to prove that this is a group, then you can apply it on triangles. You can start with, so all of them are functions. So ultimately you can write it like R composition F. That means you have written like this. This is again composition R composition F. Then again, this is R composition F. Now apply with a triangle. 1, 2, 3. And check what will happen. Now you can understand that since you are doing, you are applying this R and F on a triangle, ultimately you will end up with some rotation or flip of this. Okay, how to prove this? The proof is also very easy. Like, you have to remember this relation, why this relation is very important. Now you will able to understand why this relation is important. So here what you are having, R square F composition R square F composition. So here you have R composition F, right? Now you just consider this R square F composition R square. Now you take this one FR composition RF, right? You have taken this one. Now what is FR? FR is nothing but your, according to your definition of, or according to your relation, FR is nothing but R square F. So this is R square F composition R square. This is R square F composition RF, right? So it will be R to the power 4. That means ultimately it becomes RF. So R square F composition R to the power 4F. R to the power 4 means R, because R cube equal to 1. RF composition RF. Okay. Now in that way you can reduce the whole thing, and ultimately, so here you have FR. So now you can replace this FR by say R square FR. FR means your R square F. So R square F into then again F composition RF. So you can understand this becomes R. So this is RF. Again this is FR and then F. So this becomes R cube and then R, then this F, and then again two F's are consecutive. So this becomes F square. And what is this F square? F square means E. That means R, E, and then RF. And then ultimately R square of F. So what you will get? You will get that ultimately, even if I have whole cube of that, ultimately it reduces to R square of F. The same thing whose cube we have already started with. That means it's just an example. It's not a proof that these operations give you a group structure. So this is just an hands-on experience that how it actually forms and why this relation is important. Using this relation, you can simplify any element. Okay, now quickly, can anybody tell me what is the value of r square f into rf square. What is this value? Simplified form, because this is not an element of this, right? So I need to simplify this so that it should be like this element. It should like, so what is the simplified form of this? R square f into rf square. Simplified form means they must, it should look like one of the elements of G. It should look like one of the elements of G. Quickly, because this kind of questions are frequently asked in competitive exams. They give you some expression and then they ask what are the simplified forms.
Sir, RF.
Okay, somebody says R. Is it clear to all of you? Is it RF correct? Let us try. So R square F, so this is FR, right? So you can replace this FR by, okay, I can replace this. So initially I had R square, then FR means R square F. And then again we have F square. F square is already E. And R to the power 4 means R. So this is E. R to the power 4 means R. Sorry, R to the power 4 means R. F is already there and F square is E. So ultimate answer will be RF. So now you have some confidence that, okay, it might form a group. Okay, and really it forms a group because using this you can draw the Calais table. For example, you can start with this table. You can define this operation like this, and you start with E R R square F R F R square F. Similarly, E R R square F R F R square F. Okay. Then you can, by using this simplified formula, you can simplify it and you will see that none of this composition will go out of this 6 elements, and that will make you a closure property and proves that, okay, that gives you really a group. So you can, I will do the simplest part of it. If I multiply it with by E, then it becomes E R R square F R F and R square F. Similarly for the column, you will have R R square F R F R square F, and you need to fill up all the remaining things, and you will find that at the end of the day, after the simplified form, as I just now mentioned, by using this kind of formulae, you will suddenly end up with similar looking elements like all these 6 elements. So your table will suddenly be filled up with all the 6 elements, nothing else, and that will ensure that, okay, all the elements or all the operations that you are performing are basically is closed with respect to that. And of course this will give you the idea that, okay, all the associative properties are also satisfied. You can find the inverse element from here. So this is basically the Calais table. So from here you can, if I have one element, then you can certainly find the what would be the inverse of some element, and then you can also find that what is the identity element. So what is the identity element of that group?
E.
E.
E. E is the identity element of that group. Okay. So it's your small homework. It looks tedious, but if you are able to do that, then your calculation speed will be verified, and you have to calculate it correctly. And then there are plenty of operations or plenty of information that you will find from this table. Okay. So up to that is clear to all of you. Any question or comments or doubts? If you have, please do not hesitate to ask me. Okay, so till now we have given one example of a finite group having 6 elements. So the order of the group is 6, right? Now let us try to have a look at the same group in a different way. Just have a look at, I have already given you another way of writing the same operation. For example, I started with E and I wrote it E as 1 2 3 1 2 3. So it was like a permutation notation. For example, what I have taken like this. Maybe I can write it here. Okay, maybe, yeah, so I can write it here maybe. So the identity element was like this: 1 goes to 1, 2 goes to 2, and 3 goes to 3. So I'll write here. So E was my 1 goes, so 1 goes to 1, 2 goes to 2, 3 goes to 3. And then I started with R. What was my R? My R was like, this was my R, right? So this was my R. So 2 3 1. So R was my 2 3 1. 1 2 3 2 3 1. What was my R square? 1 2 3. R square was my
312.
312. Similarly, I had F1, which I later on replaced it by F. And what was my F? Can tell me? F was the vertical one. That means 1 remains the same and 2 3 were shuffled. So 3 and 2, right? It was my A for F1. Similarly, I had F2, and later on I have seen that F2 is nothing but, what was my F2? F2 was,
E.
no,
Oh, sorry, F2.
F2 was my, I have just written
213.
here.
213.
Okay, just a minute. So this is my F2, and F2 was nothing but R square F1. That means R square F1. That means R square F, because I wrote F1 by F, and by permutation it was, let's see how the permutation notation looks like. For F2, yeah, it was my F2, and here 3 was the fixed one. So 3 was the fixed one, and 2 1. And next F3. So F3 was suddenly F of R, 1 2 3, and here 2 was the fixed, and here 3 1. Okay, so now you can see that all the 6 elements are being encoded by another symbols like this. So I just make this as a collection like E 1 2 3. So E is nothing but my 1 2 3 1 2 3, and then 1 2 3 2 3 1 1 2 3 3 1 2, and then 1 2 3 1 3 2 1 2 3 2 1 3, and then 1 2 3 3 2 1. So the same thing, but in a different notations, right? Now the question is, what is this notation stands for? Now it will be clear that if this permutation, so this is nothing but is a mapping. So it's a mapping from a set 1 2 3 to another set 1 2 3, and if I write is as a function, and if I call this function name as my f, then f is given by f1 equal to 1, f2 equal to 2, and f3 equal to 3. So now you can see that this f, if I define like this, then this is a bijective mapping. And we all know that the permutation is nothing but a bijective mapping. So E is nothing but a permutation. So physically, what does E means? E means I started with a cake, I just cut it down, I took it out, and then I just placed it back here. So it actually filled up the hole just as it was, like 1 2 3 was there, and after filling up, this 1 2 3 remains the same. That's why 1 goes to 1, 2 goes to 2, and 3 goes to 3. Similarly, this notation stands for if I have 1, 2, 3 here, and if I also have 1, 2, 3 here, this map, say if I call it E, say F1 or say G1, if I write it like G1, if I call it as G2, then G2 function maps like this: 1 goes to 2, sorry, G2 goes to 2 goes to 3, and G3 goes to 1. So that is also a bijective mapping, right? So this is nothing but the collection of all bijective mappings on 3 elements. Now on 3 elements, how many bijective mappings that you can construct? 3 factorial, and 3 factorial is nothing but 6. And these are all possible bijective mappings from 1 to 3 onto 1 to 3. So they are the all 6. Okay, and surprisingly, this forms also a group. So collection of all these 6 elements, which are nothing but the permutations on 3 elements, that also forms a group, and that group is known as S3. That is symmetric group. Symmetric group on 3 elements. Now you can see that these two groups, though they look differently, one group is like with R and F and E, but here it's a group with 6 elements, but though they are different, that's why it's abstract. They look totally different. One is obtained just by rotating a cake or something, a triangle, equilateral triangle. Another one is obtained just by a permutation. So how this permutation actually performs here? So if you have two permutation, for example, if I have 1, 2, 3, 2, 3, 1, composition of another permutation, say 1, say 3, 2, can anybody tell me what would be this permutation becomes? Can anybody tell me what would be the permutation here? Anybody, any idea? So that is very
So
important.
one,
Let's
1, 2,
see.
3, and 2, 1, 3.
3, 2, 1.
Okay,
Two
so you
one
have
three,
to,
sir.
okay, somebody says 2, 1, 3. Let me check. Okay, first of all, this is a function. As you understand, this is a permutation, this is another permutation. So f is a function from 1 to 3 onto another set 1 to 3, right? G is again a function from 1 to 3 onto 1 to 3, right? Now when I write G, f composition G, when I write f composition G, so this will also a function from 1 to 3 to 1 to 3, clearly. Now what is m composition G of evaluated at 1? That means f of G of 1, right? So what is f of G of 1? What is G of 1? G of 1 means here, so here G of 1 goes to 1. That means f of G of 1 is 1. Now what is f of 1? F of 1 is nothing but 2. So this is 2. So G composed f of 1 ultimately goes to 2. That means after composition 1 goes to 2. Clear? Similarly, if I have f compose G of 2, then what is this? F of
1.
G of 2. Yes, tell me what is G of 2?
G of 2 is 3 and f of 3 is 1.
F of 3 is 1. So it becomes 1. So if both of them are fixed, then that will go to 3. So you can see that again this is a permutation. Composition of 2 elements is again a permutation on 3 elements. Okay. So is that clear? Is this composition clear? Now quickly can tell me on 4 elements. Is the operation clear to all of you? Any
Yes, sir.
any everybody? Any question, comments? Okay. If not, quickly tell me what would be this value on 4 elements. 2, 3, 4. Say 3, 2, 1, 4. Composition 1, 2, 3, 4. Say 4, 1, 2, 3. Tell me what would be this value quickly.
So
What
four
would be?
three one two. 4312.
Okay, somebody says 4312. Somebody says 4321. Any other answer?
4321.
Okay,
Sir, 4321.
4321. Okay, let's see. So how to check it quickly? So as I mentioned, if it is f and g, then start with this side, not from this side, because it's a function f of g of x. Many of the students, they do have a confusion from where to start. Just think about, this is a function, this is again a function, and if you have f compose gx, then by definition it should be, it should be f of g of x. That means first you need to evaluate at g, and then you need to evaluate on f. So that means you start with this side first. So 1 goes to 4, and then check where this 4 goes to 4. So 1 goes to 4 here, and then check where this 4 goes, and here you see that 4 goes to 4. So ultimately 1 goes to 4. Okay, then start with 2. 2 goes to 1, and here 1 goes to 3. So ultimately 2 goes to 3. Then it's 3 goes to, then 3 goes to 2, and here 2 goes to 2. That means 3 goes to 2. So it is correct. 3 goes to 2. This one is wrong. Again, I am saying 3 goes to 2, and then check where this 2 goes. 2 goes to 2. So ultimately 3 goes to 2. So whoever told me this one is correct and all 3 elements are fixed, then it has to be the turn for 1. Again, you can check 4 goes to 3, and then 3 goes to 1. That means 4 ultimately goes to 1. 4 goes to 1. So the correct answer will be 1, 2, 3, 4, 4, 3, 2, 1. So can who told the wrong answer? Can you just make out who told me the wrong answer? Well, you can do whatever maybe. It's not a offense. I mean, you can always make mistakes. But now I think it's clear to you, right? Is it clear? Is the operation clear to all of you? Any doubt or question? If not so, then tell me with 5 elements. Not 2, 1. Okay, tell me this one. What would be this value? Quickly. Is the permutation clear to all of you? Now tell me what would be this value.
Four
So
five
4,
two
5,
three one.
2, 3, 1.
45231.
45231.
45231.
Okay, let's check. So as I mentioned, start with this side. So 1 goes to 4, and then check where this 4 goes. 4 goes to 4. So ultimately 1 goes to 4. First one is correct. Then check 2 goes to 5, and then check where 5 goes. 5 goes to 5, then 2 goes to 5 is fine. Then 3 goes to 1, and then 1 goes to 2. That means 3 goes to 2 is correct. 4 goes to 2, 2 goes to 3, so 4 goes to 3, and suddenly 5 goes to 3, and 3 goes to 1. So this very good. Now it's clear to all of you? Okay,
Yes, sir.
good. Now let's have a look at, so we are actually trying to find some properties of group theory, right? So now S3 is already, you have seen that it has elements like E, 1, 2, 3, There's then 2, 3, 1, then 1, 2, 3, then 3, 1, 2, and then 1, 2, 3, 1 fixed, and here 3, 2, then 1, 2, 3, 2 fixed, then 3, 1, and then 1, 2, 3, 3 fixed, 2, 1, right? So they are the 6 elements. Now you may find that, okay, why should I write all the numbers in this way? Why not any simplified form? Now I'm going to show you another very important way of writing these permutations in a very simple way, and that is known as cycle notation. Cycle notations. And that's very important. Most of the books, they actually prefer to write in this way. So how to write it? Start with any. Say, for example, start with 1. So what I start with 1 and then check where 1 goes. 1 goes to 2, right? And then check where 2 goes. 2 goes to 3. And then check where 3 goes. 3 goes to 1. If 3 goes to 1, then the cycle is closed. Clear? Again repeating for this. So start with 1. So 1 goes to 3. Okay. And then check where 3 goes. 3 goes to 2. And then check where 2 goes. 2 goes to 1. 2 goes to 1. Same, starting with the same element. That means the cycle will be closed. Okay. Now what's about this? So this is this and this is this. So 1 goes to 1. If same element goes to same element, you do not need to write it down. So 1 goes to 1 means you do not need to write. Just go to 2. Okay. Then 2 goes to 3. Okay. And then 3 goes to 2. Comes to the same element here. Or some authors prefer to write like this. Sorry. 1 goes to 1 means it's a cycle closed, and then 2 and 3. Similarly here, can you tell me what should be this notation, cycle notation?
1, 3, and 2.
1, 3.
1, 3, and 2.
Okay, 1, 3, and then this is 2, 1, 2. Okay, is the cycle notation clear to all of you? Clear? Okay. Now tell me, what would be the inverse of this? 1, 2, 3, 2, 3, 1. What is the multiplicative? What is the inverse of this? So
Like
as
the
you know,
rows will rotate.
yeah. So the idea here is to find some element, another permutation, such that if I have this 1, 2, 3, 2, 3, 1 composition of that permutation, something that I don't know, that we are going to find, that should be equal to 1, 2, 3, that unknown, into 1, 2, 3, 2, 3, 1 should be equal to the identity element. What is the identity element here? This one, E. That means 1 goes to 1, 2 goes to 2, 3 goes to 3. 1, 2, 3, 1 goes to 1, 2 goes to 2, 3 goes to, like your birthday cake. You just cut it out and just place it the exact position. That means 1 goes to 1, 2 goes to 2, 3 goes to 3. That is the identity element. That means it should like 1, 2, 3, 1, 2, 3. Okay. So what is this element then? Can anybody tell me what should be the inverse of this?
3, 1, 2.
Okay, somebody says 3, 1, 2. Now can quickly somebody check this composition. So those who are having even roll number, check this product. What is this product? And those who are having the odd roll number, check with this and tell me whether they are getting this value, this identity or not. That means those who are having even roll number, check with this product, and those who are odd roll number, check with this product and tell me whether this value is equal to this or not.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Very good. Okay. Now, so you very quickly you just made it. Is it clear to all of you how he made this? Can anybody tell me how you made this? How you quickly get this value?
So, sir, I will tell, like, suppose you just inverse the, like, you just interchange the rows. That's the main logic.
So how
Like,
to
you
interchange
just,
this?
for 2, you just write 1. Like, from the lower row, if you take 2 and the upper thing is 1, so you just write 2. For 2, you write 1. For 3, you write 2. For 1, you write
Oh,
3.
okay. So in S5, so in say in S5, try to find this inverse. Say 5. Okay. The inverse of this, what is the inverse? Tell me this blank value.
43215.
So you're saying 4, 3, 2, 1, 5. This one. That means
Yes.
self-inverse. You're talking about this is self-inverse. Okay, anybody else? Is it correct?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so I'm going to show you a very simple technique how to get this inverse. Okay, first write it down in cyclic form. So what is its cyclic form? 1 goes to 4, then 4 goes to 1. That means this is done, right? And then 2 goes to 3. Then start with any other symbol which are not there. So 2 goes to 3 and then 3 goes to 2. So it's done. And then 5 goes to 5. As I mentioned, if the same symbol goes to the same symbol, you do not need to write it down. So what you want the inverse of this, right? And what is that inverse? Remember, this inverse is nothing but 2, 3. Just you need to interchange. I mean, you just need to write it down like this. You just, if it is AB inverse, same as B inverse, A inverse, not like A inverse, B inverse. So for general group, this is the rule that you have already seen this. So in the book, you have already read this part that A in any group, AB whole inverse equal to B inverse A inverse. So here also the same thing. So this is B inverse A inverse 1 4 inverse. Now what is the inverse of this? Okay. For any inverse of a cycle, you just write it down on the other way around. So it starts from 2 3, you starts from here. That means like this. So the inverse of this is nothing but 3 and then 2. So inverse of this is nothing but 4 and then 1. So if I write it like this way, say 1 2 3 inverse, what is that inverse? You just start from this 3 and go in that way. That means 3 2 1 is the inverse of 1 2 3. Okay. Now just check what happens here. So here 3 goes to 2, 3 goes to 2, and then 2 goes to 3, 2 goes to 3. Here 4 goes to 1, 4 goes to 1, and 1 goes to 4. And since 5 is not present, that means 5 must go to 5. 5 is the 5. So that's the inverse of this. Is it clear to all of you? Clear?
Yes, sir.
Now,
Yes.
okay. Any question or anybody? Please do not hesitate to stop me. Otherwise, you will be the loser, not me.
So just a question.
Yeah.
Yeah, so like the method I told you, like interchange the rows, was it correct, sir?
Yeah. So
Okay.
what was your interchanging the rows? Can you explain once again? Suppose I want to make an inverse of say 1, 2, 3, 4, 5. Say I want to make an inverse of say 5, 3, 2, 1, and then 4. Can you make an inverse of
Yes,
so
sir.
okay.
Like if we just I'm like the main thing is you just interchange the rows. Like for 5 you write 1, for 3 you write 2, for 2 you write 3, for 1 you write 4, and for 4 you write 5, like that.
Okay. You just make it like this in that way.
Yes,
So
yes, sir.
so 5 what should I write here? 1
5,
means 4.
5, 1 means
So
4,
here 4 and then
2,
2
3, 3,
3
for 3,
and then 3 is 2
2,
and
3 is
then
5, and 5
4 is
is
5 and then 5 is 1.
1.
Okay. So what she is doing is basically just revert it back, and that will be the inverse. So in our way, what I write, if I write it in symbols like cycle symbol, 1 goes to 5, 5 goes to 4, 4 goes to 1, right? So the symbol is closed, and then 2 goes to 3, and then 3 goes to 2. So whole inverse. And just now I mentioned A B inverse means B inverse A inverse, that means 2 3 inverse composition 1 5 4 inverse. And what is that 2 3 inverse? 2 3 inverse, you just write it in the other way around, and this is 4 5 1. And just have a look at this. So 3 goes to 2, 3 goes to 2, 2 goes to 3, same thing. And then 4 goes to 5, 4 goes to 5, 5 goes to 1, 5 goes to 1, and 1 goes to 4. 1 goes to 4. Exactly the same thing. So whichever method that you find more comfortable to write, because for most of the problems are asked in this cyclic form. So one thing you can do, you can convert it into this form, and then you can whatever is easier or simpler to you, you are welcome to do. The only thing is that you need to do it correctly, otherwise the marks will be deducted. Okay. So that's the only point. That's why you can see that in many of your competitive exams you do quite well, but when you will find the keys or answers to that questions, that you will find that you committed many of the silly mistakes. So one of the reasons behind is that you are not very good in doing this calculations properly. So unless you do some practices, it would be not very possible for you to do it correctly. So that's a kind of practice that you always do. Otherwise, you won't be able to do that. So now it's very clear to all of you. Okay. So regarding S3, you get many information. Now tell me what would be the order of the Sn for arbitrary n, where n is greater than equal to say 2. What would be this number? Order of Sn?
N factorial.
Yes. So just now we have seen that it's nothing but collection of all permutations on n elements. So Sn is nothing but the order of Sn will be n factorial. Okay. So that's very important. So S3 we have seen in two different ways. One in this way, in a nutshell, if I just recap once more, then we have flip, then RF, then R square F, and in our normal way E, then 1 2 3 1 3 2, then if I drop 1, then we have 2 3, if I drop 2, then we have 1 3, and if I drop 3, then we have 1 2. So both we have seen S3 in two different ways. We have also seen what do you mean by order of a group, order of a group, order of a group. So we have seen finite and infinite, finite group, example S3, or Sn, infinite, we have already seen, Z with respect to addition, Q with respect to addition, then R, maybe R star with respect to dot. R star means R minus 0. Okay. So there are two types of groups, broadly speaking, finite groups and infinite groups. Especially we have already seen for Sn what could be the inverse of an element. Inverse of an element. So in the next class, we'll do another very interesting thing that is known as order of an element of any group. Order of an element. So I just request all of you to please have a look at any book from my book or Galleon book or from Damit Food, any book. What do you mean by order of an element in any group G? Okay. But before I stop my lectures, let me check a few things. Like it's basically a very simple question, and I will ask you this question, and you will have to answer me in the chat box. Okay, in the chat box, you will just write the answer. This kind of questions. Why I'm doing this? Because through this classes also, I am going to give you a preparation for the competitive exams like JAM or TIF or NBHM. So there you have to calculate. Okay, you have to give some answers, and you will have to give the answer quickly, right? You don't have infinite amount of time so that you can learn or you can do whatever you want with longer time. So there must be some time limitation. So the question is very simple. You know rational numbers. The question is, can you find or what is? So I am giving you one interval, half and 2 by 3. Okay. So my question is, find the rational number in this interval having smallest denominator. Okay, so what you need to do, you need to find some rational number within this interval. So this is, mind that this is an open interval. Within this interval, whose denominator, that means a rational number must be of this form p by q, where p, q are integers, q not equal to 0. What you need to find are the rational number whose denominator is minimum. Can you quickly tell me what would be the answer? Is the question clear? Find the rational number in half and 2 by 3 having smallest denominator. So this should be the smallest, but it should also lie within this interval. In the chat box, quickly give me your answers. Is the question clear to all of you?
So it is an open interval only.
Yes, it's open interval. Okay, somebody says 1 by 3. Okay, let's see what are the answers. It should be within that interval, right? So 1 by 3 is not within this interval. 1 by 3 is not within this interval. 1 by 3 must be here somewhere. To write like this, so it should be half and 2 by 3. 1 by 3 lies here. 1 by 3 is strictly less than half. So within this interval, it has to be, as well as
So can it be 51, like 0.51? No, no.
So it has to be rational number. It should be in a P by Q form.
So 7 by 12.
Okay, somebody says 7 by 12. Okay, many of you have already given 7 by 12. Anything else? So all of you. So you all know rational numbers and you all know calculations. You all know what do you mean by the smallest denominator. So come on.
So 3 by 5 হবে?
Okay, somebody says 3 by 5. Suddenly, this is better than this, right? So whoever told 7 by 12, he has given better answer. Anybody else? Or are you sure that it will be 3 by 5? It's Rahul Ahmed.
Yes, sir.
You get that? You also gave 3 by 5.
Yes, sir.
Good. So it's a 3 by 5. And see, you can see this. It's a grade 5 monthly problem sets. It's a 5, class 5 problem. And it came in second month. This problem. Now, can you see that the question that I asked you is for actually grade 5 and it came, and many of you are unable to solve this problem. Many of you have given the wrong answer even, and few of you have given the correct answer. So that means for competitive exam, when you are under time pressure, sometimes you may not work properly. And that's why you will find different results, outcomes of the exam. You may be good in mathematics, but sometimes it happens that you are unable to solve the problems within a time pressure. So you have to be good in calculations as well as theory. Because I have seen many of the students who dislike writing, who dislike bigger calculations. But unfortunately, for many of the competitive exams, for example, the JAM or somewhere, you have to carry out some calculations. And those who do not like these calculations may not be able to get good score in JAM exam. So it's my request to all of you, you should increase your ability to do calculation quickly and correctly. You may do it very quickly, but your answer is wrong. It's nothing. You may be very good in calculation, but you are very slow. Then also you will have a problem. So you need a speed as well as the answer should be correct. So that's the idea. So with that, I end my lecture here. So if you have any question, please let me know.